That's the one I
Let's
told
go.
you.
Yeah, I figured it out.
And I didn't tell you.
No, I figured it out.
Oh,
on
maybe
AC.
that's-
Yeah,
Oh,
probably
yeah.
not. Yeah.
Like I was in six, like,
Alright guys, this is the last lecture, last tutorial. Probably need another lecture on Friday, but this will be short, and also the solution, the code is given, so I don't think there will be a lot of stress on that. But very important concept we covered, so you guys need to know what's really happening over here. And today's lecture may be short. Why is that? Because I was not able to finish the tutorial. I tried so hard. Maybe 80% of it done. Okay. So Friday we'll cover more. So the concept here is that we want to record audio signal to the SD card. If you think about that, you are using a ADC to sample data. It's probably for one of the senior SAM teams, maybe Luke's team. So they are doing some testing and ADC sampling, data acquisition. So the data acquisition is at a pretty high speed. So in that case, you need to sample it and store it onto the SD card. And just in case, right after it, you want to play it back. If it's a speaker, that's actually a perfect example for the digital decoders, right? The sound decoders for the trains. It's basically a digital signal being output to from the memory. And how do you play a analog sound through a digital signal? So that's a question about that, right? So when you play it back, just using all the resources on the scatboard. So there's a really interesting effect you want to know. It's about physics, okay? Remember we talked about time delay. I mean, in VLSI or in circuit 1, we have talked about time delay. If you have a digital signal like this going through an RC circuit, what's the time delay of it? 0.7 RC, right? There's a time delay. So the reason for that is it takes a finite amount of time to charge up the cap and then discharge like this. So the input here, so input digital signal, and it's getting delayed, right? No one can avoid that on the circuits. If you're not using superconductors, there will be time delay. Okay, there will be time delay. So parasitic resistance and capacitors are everywhere, and so time delay is usually a very bad thing to avoid. And you have to design your circuit very carefully. Try to, improve the performance of the circuit. However, if you are using a low-pass filter, and the purpose of using the low-pass filter is to create a sine wave or create any arbitrary signal from that digital signal input, and then you are using the time delay to form different signals. It's very interesting. So here we know how to output PWMs, right? If you adjust your PWM in real time, the duty cycle in real time, and whenever you have a wider on time, you got a bigger output voltage. That makes sense, right? Because it's able to charge up the cap more efficiently. But I have to adjust it more carefully. You can see the area over here, you have a higher voltage of the sine wave. And in this period, definitely you have a wider on time. So when you want to decrease the voltage, you're just slowly giving a lower on time. Okay, so if you modify this PWM into a certain pattern, you will be able to create any frequency of analog signals. It's really interesting. And another interesting thing is that, think about that. So if you use an ADC to sample an audio signal, right? Sample audio signal. So it will be discrete points to be sampled and being stored in the memory. So these are actually bytes, right? So you got a continuous analog signal input, and then eventually you have every single point, or most of the points being sampled and being stored in the memory. So you're getting bytes in the memory. The bytes in the memory. So when you play it back, magically, if you use that, because bytes are from 0 to 255. You agree with that? If you are using an 8-bit, I mean, I know it's a 12-bit, but we are just using 8 bits, right? Just 8 bits resolution, right? So the final result will be from 0 to 255. And you can use that number as a duty cycle, as a duty value for your PWM module, and directly throw it to the speaker, and it's going to play the audio for you. Do you know what I'm saying? So you sampled it, right? You sampled it. And that sample data is actually falls into the range of the 8 bits. And that becomes 0 to 255. No problem on that, right? It's 8-bit resolution. So the analog signal will be sampled and being digitized, and the numbers will be from 0 to 255, any numbers depending on the voltage. And that number is the digital conversion, is a conversion of the analog signal. But there's nothing to do with the PWM. Okay? However, if you put that number and assign it to OC, let's take a look. OC what? Remember? Do you remember that? OC RNX. Good job. OC RNX as a duty value, and directly throw that PWM to the speaker, and it's gonna play that back. So why that? It's not exactly the pitch. You know, when you play piano, whoever can play piano a little bit, sort of, okay? So you know that if you do do, re, mi, fa, sol, la, si, right? Or you can increase the pitch for is that called octal?
Yeah,
Octal, right? But it sounds the same, so it's all relative. You know what I mean? So even though the pitch is slightly different, but because it's playing all the relative differences of the notes, so eventually you are hearing pretty much the same thing, even though there's probably different octals that are playing the different octals. That's why it still works, right? It's magically it works. It's a really interesting experiment. So I was working on getting that code ready for you guys so you can directly use it. And some of you guys are, trying to do a project on playing back an audio. Definitely it's doable because the code will be available for you. I'll just let you change a little bit on that. But for the hardware part of the circuit, you don't have to change anything. Okay, just keep in mind that for your PCB, I haven't submitted yet. I'm gonna do it tonight, for sure. Otherwise, it's gonna be delayed. So, for your audio amplifier sampling, it's over here. So you need to use this module for sure. As the module is shorted to ADC0, you have to digitize it, right? So, no doubt on that. And when you play it back, you will need this module here, the two modules over here, the IC card. You need to store it over there and then play it back. And also you'll need an audio amplifier and low pass filter. You need this guy and this guy. Okay, so I'm using PE3 over here, and PE3 on the Skyboard is actually the one. So it's JP6, right? JP6 is a jumper number 6 and has a PE3 connected to it. So where is JP3? It's actually over here. It's really confusing because it was not labeled properly. So in Skyboard version 3, we have to fix a lot of things. But anyway, you can see JP4 is actually from here to, I think six pins maybe. 1, 2, 3, 4, 5, 6. So 6 pins is JP4, and these 2 pins over here are JP6. These are JP6. See where that is? This is a chip, right? These are all the header pins, and that's JP6. So where is JP5? JP5 is the output of the audio amplifier. The low pass filter. JP5 is over here. That's JP5. So if you put a jumper on both headers, the jumpers are shorting these 2 pins and these 2 pins separately, what's going to happen? So your PE3, which is the pin on the microcontroller, that output will be shorted, will be connected to the input of the low pass filter. All right, and then you are getting a filtered result at this pin, but you still have to put a jumper here as well. So that's JP5, that's JP6. You're shorting these two pins, and then you can deliver the result to PRE. So pre-amplification. So pre is actually here, shorted to here physically. There's no header pin on it. It's just a trace. It's getting labeled as name pre, and same name will have them physically shorted to each other on the board. Okay, you're not changing anything over here. So the thing is, if you put a jumper here and here, it's directly getting the filter result from the PE3 to the input of the audio amplifier. So this is the audio amplifier. Okay? And that's the speaker's connector. So PE3 is shorted to where? So what is the PE3 pin? Pin map, right? PE3. I mean, it's by chance, it's the same pin number, but that's the pin number of the chip, and that's the pin number on the Arduino board. It's labeled on your SkyBoard, right? This is pin 5. So pin 5 is the PWM output, which makes sense, right? Since we are trying to use that as a function generator, we can output a modified PWM signal in order to create any frequencies of sound waves, right? So P3 is actually a pin 5, and that's the OC3A module. What does that mean? That's a PWM module 3. It's controlled by timer 3. But we don't have to worry about that. It's a PWM module 3 A. It's not B, not C. It's A. It's PWM module 3A. So when you are doing your PWM programming, okay, so these kind of things will be put on the final exams, right? So I'm going to give you an example about like which pin I'm going to use for this example, and then you modify the registers. I'll give you the registers as attachment, but you still have to figure out how to do it. So let's take a look at these tables. All right. It is, so we are going to use a non-inverting mode, so we are able to use this diagram for our design. So what's the top register? Which one defines the top? ICR3. Okay, ICR3. So which one defines the duty value? OCR3B. No, OCR3A. Why? Because it's the OCR3A. It's OC3A module. So it has to be OCR3A. So in your code, you are actually assigning a value to OCR3A. And you are defining ICR3 as a top. So one quick question over here, okay? So if you look at the code, it's given, and someone created a table, an array here. It was already given. So given that this array, all the numbers here as a PWM duty cycles value, the duty values, and you can see the maximum is 255. So you can tell it's actually from 0 to 255. These are the duty values defines the duty cycles. Okay, so we don't have time to create the sine wave, by ourselves. So it's given. So these duty values, if you directly give it to the PWM and assigning all these duty values at a certain time, and it's going to output a sine wave for you. I just let you know. Okay. So these are the values you want to use. So you can see the top is actually 255. The maximum value is 255. So for our PWM module, the non-inverting module over here, where is it? Where is it? No, it's over here. For here, given that table, given that array, okay, what value you want to use for ICR3? Because these values are defining the duty cycles, right? The duty cycles. And we have 2 to the 16th counts in the register. You can use, so the TCNT3, it's a 16-bit timer, and you have 2 to the 16th, the maximum count. You know what I mean? So if you draw that TC and T3, it's that big, right? It's that big. So the maximum count is 2 to the 16th minus 1. Okay? You have so many numbers to use. You can count towards the maximum, but we are not. Since we don't have the time to find out to map all the numbers in the sine wave array to this maximum number, so the given number is from 0 to 255. So it's basically changing the duty cycle from 0 to the full cycle here. So what's the top number you want to use for ICR1, RCR3? Because these 0 to 255 are the numbers in the code. It's given. That's the sine wave PWM output. It's given here, right? We know this from somewhere, right? It's given. Which top value should use for the counting? Which top value should use for that little non-inverting mode here, right? In the top, you need a duty cycle, right? So duty cycle is changing. You are basically assigning all these values to OCR3A, right? So throwing all these duty cycles to it at a certain time, so you can change the PWM over time to create the sine wave, right? You are throwing these numbers over there, during at a certain frequency.
So this top should be 255.
Yeah, 255. I think probably the question is too simple. That's why it's just 255. What did we use? What did we use last time? I think that was like 400 or 399 or something, right? So we picked up that one to define the frequency of what? Of the PWM for IR, right? Remember the IR requires, right? So the IR requires what? 38 kHz? I forgot. 30 something kHz, right? And we find out the top value for this frequency, and now we are not doing that anymore, but we can modify it. So since we know the duty cycles, duty values are changing from 0 to 255, let's just choose 255 as the top. So it's either outputting 0 or outputting 1. Does that make sense? Okay. So low pass filter and the circuit, this is pretty much the same schematic, but with the unknown values of the R and C's. And that's the DC gain. These define the frequency, and this is the DC gain. And you can tell that the amplifiers. So quick question over here for you guys. Is this a negative feedback or a positive feedback? You don't even think about it. All the amplifiers has to be negative feedback. It has to be negative feedback. So this is a non-inverting. It doesn't matter. It's inverting or non-inverting. It's just a negative feedback over here. So you are looking at the negative feedback resistors to find out the voltage gain, right? So the voltage gain defines the DC gain. So if you have the frequency, if the frequency is not too high, or at the DC level or pretty low frequency, and it's not attenuating the signal by the corner for the frequency response curve defined by the resistors and capacitors over here, it's getting complicated. I'm sorry for that. If I haven't done that too much, it's just overwhelming. But it's just so fundamental. Okay, so the conclusion is that if you are looking at this circuit, and you know it's a low pass filter, and you should know that if the frequency of the input is not very high, it's below the corner frequency over here, so it's not getting attenuated, then the gain will be what? The gain of the voltage will be what? This will be on the finals. What is the gain? The gain is really simple. The gain is just a RA over RB. That's it. Maybe -1, but it can be ignored because it's usually the gain is more than 10, right? So it's basically just RA over RB. That's the DC gain. So for our schematic, what is our DC gain? Huh? 1. Because this is what? Over here. What is this called? It's a voltage follower. It's a voltage follower. That's why the DC gain is 1. Okay? So what is a voltage follower? It's really simple. It's used as a buffer for a lot of times. Always negative feedback. Output goes to the negative input. V in, V out. And V in equals V out. It's a voltage follower. So the benefit of doing that is you can separate your output from the input. You can see these two inputs, they are totally separated. So you have a super high impedance in the middle between the input and output. So whenever you are outputting a, for example, a voltage divider, it's not affecting whatever the voltage divider resistors network in the input. It's totally separated. It's used as a to separate the input and output, and also used as a buffer. So you can have a more power supply, you know, kind of source power from the VDD and ground. Okay. So this circuit on the schematic is a voltage follower over here. So the DC gain is 1. It's actually not amplifying anything. However, it has the corner frequency. If you look at the curve here, this is the frequency response, which means whenever the frequency of the input is higher than a certain frequency over here, and it's going to attenuate the output. So this frequency over here is called a corner frequency, and also from here to here is also referred as the bandwidth of the circuit. Okay, so that's the bandwidth. If it's any frequency outside of the bandwidth, it won't be received without attenuation. So you can see high frequency will be attenuated even further, and that is all because it's a low pass filter. Okay, so the low pass filter has a corner frequency which can be calculated. If you have all the R's and C's are the same, right? R1 equals R2, C1 equals C2, and eventually the corner frequency can be calculated as 1 over 2 pi RC. It's a conclusion. We are not deriving everything from scratch. We don't have time to do it. So it's 1 over 2 pi RC will be the corner frequency. So if you calculate our corner frequency, you'll be able to find out the answer for one of the questions on the in class, right? What is that one? It's question number 1, actually. Okay, do a quick calculation and find out the frequency of that. So this may answer the confusion or conclusion that when you play with the amplifier, the audio amplifier and the speaker, sometimes you're getting a really low volume. It's probably because the frequency is too high. If it's way higher than whatever the corner frequency you calculate over here, it definitely will be attenuated and the volume will be low. Okay. How do you amplify it? Here's the audio amplifier, and I didn't look into the data sheet, but there might be an equation to calculate the gain of the audio, because the audio amplifier is supposed to amplify the audio signal, right? Whatever audio signal output from here should be amplified. So it should allow you to modify the gain of the amplification. Okay, you can refer to the data sheet to find out the amplification. If you think the volume is too low, you can probably simply swap the two resistors. I think if you look at the input, this is a minus in, so I think very likely it's going to be R12. If you choose 100K, probably it's going to amplify it even further. And the reason we didn't do that is it's probably the amplification is already enough, you know, so it's not saturating our VDD. Otherwise, it's getting cut on the top or bottom, which is bad. So it's losing information from the signal. So as long as it works, you know, just use this gain we have. You can always modify it if you need to. All right, so we already answered 1 through 3, I think. Which mod is used for task 1? Yes, we did it. For the P11 module to be used which register defines the top, which register defines the duty value. Also did that. Okay, for timer 3, since we're using timer 3 module A, right? Timer 3 module A. So when you modify these 2 bits, so where are these 2 bits? Where are they? TCCR1A. Okay, so you can see there are A modules, B modules, C modules, and you can modify each module's mode separately because these are different bits in TCCR1A. For our case, this is going to be TCCR3A. Okay, so you can see we need the A1 or B1 or C1 bit to be 1, and the A0, B0, or C0 bit to be 0, depending on which module you are using, right? Are we using A3? It's a trap. No, that's just a bit 1. It's not timer 3. Timer 1. It's a trap. All right, so that's bit 1, bit 0. Okay. There's nothing about the timer for this number. Okay. Doesn't matter what timer is. But they will have, you know, COM 3A1, right? So for our case, it's going to be COM 3A1. And you want to set that bit to be 1. Let's see if we did it right in the code. Yeah, I did it here. Okay, so that's a number, that's a bit location. So you do this, you will turn that mode on. And for a prescaler, I use 256 as a prescaler. So there's a calculation here. If I'm using timer 3 and 256 as a prescaler, the top is 255. So if the top is 255, to reach to the top, you still need a 256 counts because it's counting from 0, right? Counting from 0. So if you use 255 as a top, so still have 256 counts. How long does it take to overflow the timer? Staring at me. You are thinking. You are thinking. All right, how to calculate it? We've done this thousands of times, right? Homework assignments and the midterms and those kind of things. All right. So the last one, number 6. What does the following code do? What does it do? So index starts from 0, for example. Right, start from 0. What is this doing? So the number being ended,
0 to 255.
0 to, no, you have 5 ones, right? So what's happening here is, if you, so this number starts from 1, for example, starting from 1, right? Start getting 0B, 0, 0, 0, 0, 0, 0, 0, 1, like that. So this must keep going until what? 0B, 0, 0, 0, 0, 0, 1. 0, 0, right? Because in this case, this and this, this and this, this and this, this and this, and this and this. So all these ones are being added to the zeros over here. Since all these are carried out, eventually got to carry out over here, right? So it has to count until this number in order to get a 0. So why do you want to get a 0? Because you can see this and this. If you get a 0, index will come back, will go back to 0, right? So it's actually cycling back to 0. So it's counting to 1 and then go back to 0. So after this number, it will start counting from 1, all of them are zeros. And I got a 1. So this ended, this guy is still a 1, right? It's cycling back. What that number is counting from 0 to what? And then come back to 0 every time. I told you the answer. It's over here. Yeah, 32. Okay? So, while we are doing that, if you look at the code, here we have 32 points. 32 points. Why 32? It doesn't have to be 32, can be any number. 25, 26, doesn't really matter. And just giving you all these numbers that I can cycle through, so you can look at the output. Right? Every time you throw a number here, you press any key on the keyboard, it's gonna increase the index and give a next duty cycle value or duty value to the PWM, so you can look at the results, right? So you can demonstrate that it works. And the way it works is, for task 1, is like this. It's really simple.
Right, tutorial number 8 and task 1. So first, you can see that I have this jumper here and this jumper here. So
this is JP what? JP6 is JP what? JP5. And you can see there's a little wire, the bare metal on the top. That's the place you want to hook up your probe of the oscilloscope tool. So you can probe things, even though it's getting covered, but it still have a metal on the top, right?
jumper here over here.
What's that?
Are those wires connected to a low-pass filter?
Yeah, so this is the output of the low-pass filter, and these are the input of the low-pass filter. The two headers, right? The JP5, the JP6, the JP5.
Is basically the input of the low-pass filter, and the one on the left, so on the left-hand side, is PE3, and the other one is the input of the low-pass filter. And the output header here is the header just behind the IR decoder over here. So if you put a jumper on the top, there's a little metal wire on the top that I can probe. You can hook this up to the little wire and probe it. Okay, so the code is provided, and you need to open a PuTTY session. And first you need to press S. And so if you press S, the duty cycle is set at 50%. So you are seeing something like this. Right?
Yeah, see, this is really familiar to you guys, right? It's just a time delay. It's a digital, it's 50% duty cycle, and you are getting a delayed output of the digital signal. I've been seeing this for a long time. It's a very simple RC low-pass filters output. And when I'm choosing a different duty value from the array, right? I'm just throwing a different number. I press any key on the keyboard, it's gonna go to the next one. It's gonna increment the index and go to the next one. So we'll change the duty cycle of the PWM. I should have that display on the channel too, but I didn't do that. But you can imagine there will be a duty cycle change.
Right, it's just basically 50% digital signal, and it's getting delayed because of the low-pass filter. And then you press any key on the keyboard, just any key on the keyboard, to cycle through all the duty cycle values in the array, and it's going to show you different time delay effects. Okay, it's cycling back.
See? Okay, so for a very small duty value, and it won't be able to charge it up to a certain voltage. That's why it's getting lower
right.
as well. It's also can be explained by the low pass filter's corner frequency, right? So when you have a super sharp spike, it's actually a high frequency component, and it will be attenuated a lot because of the low pass filter's corner frequency. Okay? But the question is, these waveforms, they don't look like a sine wave. Are we getting into a trouble? We are trying to make up a sine wave, but these don't look like a sine wave. Why?
Because of aliasing.
Huh? None of them look like sine wave. You saw all these waveforms like or sharp or short. It's not a sine wave. But aren't we trying to get a sine wave? these won't play a music, right? These signals are not music signals. We want to create any AC analog output. Could be a sine wave, could be anything, a mixed signal, any analog signal, right? It should be able to do that, but that's not. Are we getting into trouble? Are we? Are we getting into trouble? Because every time I change it, it's outputting a certain duty value, duty cycle. It's not changing. If I want to create a sine wave or any arbitrary signal with a certain frequency, it's actually always changing in real time. It's not just the one PWM. The PWM frequency is changing all the time in order to form a different sine wave. Make sense? Well, so every time I press it, every time I press the key over there, I'm just getting a certain frequency of the PWM. It's either this or a wider one. It's a constant output. It's not changing. But in order to create something like this, okay, so that OCR3N, OCR3A need to be overwritten in real time. So it's always changing the output, the frequency of the PWM. By looking at this waveform, you can see the frequency is always getting changed, right? So if you throw one, it's doing this, and another one, you keep changing it in order to form any signal you want to form, okay? That is why I'm thinking, be able to create a function generator or a signal generator is really helpful, especially nowadays for quantum computers. All these qubits are receiving any arbitrary stimuli and need to be created from a function generator. So people are using FPGAs to generate all these high frequency analog outputs, or using our microcontrollers. The only thing for microcontroller is that it's very slow, right, compared to FPGAs. So it's very slow. For high frequency analog outputs, it's probably not able to do it really well. Okay. Any questions on this? Okay, so the code for the playback version, task 2 of this tutorial, will be posted either today or tomorrow. So during tomorrow's lecture, we'll be able to cover that a little bit. But maybe I will leave a couple of blank areas to let you guys fill up, but it will be very, very simple, very simple. Also, I have a task today, which is to submit all the PCBs. If you see issues with your PCB, please make sure that you confirm with me, right? Make sure there's no problems on that. We probably don't have time to run another fabrication. So it's one and that's it. If we see issues, we'll just have to cut the traces on the PCB or making jumping wires, to try to fix it. Okay. If you have any questions on the PCB, let me know as soon as possible. Okay. That's everything for today. Did I answer all the questions on this sheet? I did. Okay. You could use the rest of the class to work on your project programming, and you can ask me questions about the project.